Okay, welcome back. So before we move forward, I wanted to spend a little bit more time on the slide which shows the central part of the V1 architecture, because it sort of demonstrates one of the most important ideas that I think P416 brings into the P4 world. And that is, you do not really need to know what's inside the component in order to properly use its functionality, in order to consume it. A lot of things that in P414 used to have their own primitives, for example, cloning or recirculation, resubmission, and so on, even dropping the packets, can be very easily done with the core language, as long as you know that there is a certain set of very well-defined metadata that talks to this component that we cannot really define in P4, but the one that we want to use. We don't really know what this packet replication engine does in the sense that it's not described in P4, but it is described in the documentation for the architecture. And so we, for example, know that if we want to send this engine to work for us and send the packet to a given egress port, we'll set this egress spec field. If we want the packet to be multicasted, we need to set mcast group field. If we want the packet to be cloned, for example, we can set the clone spec with some data, and again, what kind of data that will be and how the packet will be cloned, meaning that a second copy of the packet will be created, will be described in the definition of this red box, the packet replication engine. But the interface to this component is very, very standard. You just basically set the intrinsic metadata, and I think that is a very, very powerful concept. So, and the nice thing about this is you know exactly what's happening, so things are not abstracted from you by, for example, some primitives. So if you set the field, you know that unless you actually finished your control processing, you can still go and change this field, or you can examine this field, so they're fully available to you to do exactly what you would like to do. Let's restructure our reflector program that we saw before a little bit. And the way we'll do it, we'll basically define some actions, and that's the process that is very similar to how functions are defined in C language. First, I'll define an action to drop packets. Again, this is a definition which is very specific to V1 architecture. So in V1 architecture, if you want to drop a packet, you need to set two fields. So you need to set egress spec to some special value 511, which is a drop port, and you also have to set the multicast group to 0. I'll just define this function, and in fact I don't have to do it because if you look at the file v1model.p4, it's already defined. I just showed to you what's in there. I'll also define a couple of other functions. So for example, I'll do swapping of the MAC addresses in a separate action in the way we all were taught earlier enough in our computer science classes. So as you could see, actions can be defined either inside the control and then they become local, or they can be also defined at the top level outside of the controls. Again, the nice thing about actions, the parameters are fully typed. So you specify the type of the parameter and you also specify the direction. Although we'll see later that actions can also have directionless parameters as well. Inside the actions, you can instantiate variables if you like. You can also use some control statements. So here's another action. We'll call it reflect to another port. So what I'm doing here, just for the sake of the example, I'm flipping the last bit, the bit 0 of the port number. So if the packet comes in on port 0, it will get back on port 1. It comes in on port 1, gets back out on port 0. And so what this demonstrates is in P4, you can have expressions like in any other programming language. Normal arithmetic operations are available, logical operations are available. There is no division because we don't want to have exceptions like divided by 0. And there are some additional operations that I'll demonstrate a couple slides later, bit slicing and bit concatenation. But for now, obviously, I'm demonstrating a very simple XOR. Once I've defined my actions, What I can do, I'll just define the body of my control using these actions. Decided to do one extra improvement. As you know, on the Ethernet, it's not really legal to have multicast addresses as the source addresses. So I decided that if the packet arrived and the destination address was a multicast, I'm just going to drop the packet. Otherwise, I'll swap my MAC addresses and reflect to the other port. This allows you to structure your program nicely, and that's standard practice as in any other language. So far, so good, I hope, right? The question is why standard metadata is not specified for the mark to drop action. The answer is, right? Well, it is an out, but it's not specified there in the argument list at all. And the reason is because it is specified at the top level. When we call mark to drop, it kind of gets available to this action. That's basically done for the reasons of ease of transition. So it's not that the syntax is fully C, where you can only have access to the variables that you defined inside. In P4, actions, if you want to, they can have access to the names defined out in the outer scope. That's the reason mark to drop does not have those particular ones. Can you have action inside the actions? No. But you can define as many, and then you can call actions from another action. That is definitely possible. So here are some other things that you can do with actions, again, by using just the core language. As I mentioned before, headers have a property called validity. And so therefore, headers have special methods that are defined just for them. There is a method to make the header valid, to make it invalid, or to check if the header is valid. And what happens very often in our data plane programs that we write for the real networking devices is we need to add or remove headers from the packet because we perform some sort of tunnel encapsulation or decapsulation, or it's called initiation or termination. Here I'm just showing how I would encapsulate a packet, IPv4 specifically, in a two-label MPLS packet. This is the definition of MPLS header. It's a label and 3 other fields. What I will do, I will make the MPLS 0 valid. So that means that I have just added one MPLS header. And then I go ahead and fill in the fields the way I would like them to be. And then I will do exact same thing with the other MPLS. That's another MPLS header. I'll also add it. And here I show that I actually don't necessarily have to assign fields one by one. I can just use a tuple to assign them all together. Ultimately, for the compiler, it's probably the same thing, but I just wanted to demonstrate you a different syntax that is available for you in the language. And the last thing I want to do is I will need to change my ether type because it shouldn't be 800 anymore, it should be 8847. So here I'm showing that inside the action I even can use the if statement. And if I have a VLAN tag, then I will set the ether type inside the VLAN tag. Otherwise, I'll set the ether type right in the Ethernet header. This is a more complex action that we saw before. But actually, what's interesting is on many types of hardware, if you think about that, it can also be done in one cycle and fully parallelized. So it's actually not an outrageous example. It's very, very practical. The question is, how do I define the overall header format of the full packet? The answer is you do not really define that. It is when the packet arrives and the parser starts to parse the packet, it will find one header there or the other header, or one header followed the other header. Now, if you look at the parser program that you construct, you can sort of determine, if you do a topological sorting of the states, which header follows which. But for P4 program, it doesn't matter. The reason I decided to do this manipulation of the ether type is because I know that later on when I try to reassemble my packet back, I will need to output headers in a certain way. From P4 program standpoint, it just doesn't care. The question is, where did I define the MPLS itself? And the answer is header itself is a struct. And struct can contain an arbitrary number of members. And when you just define your struct, you just say, I want to have, for example, a stack of 5 MPLS labels, and so subsequently it will be there. You can have it predefined, and so most probably you will just put all the headers that you want to process in your program in a single struct. That's one of the options that is available, but it's not the only option. It's the same way like how you declare any other variables in C effectively. The header is valid means that the header is valid at this point in time. So when we just enter the ingress control, that probably means that the header was found by the parser, it was extracted by the parser. But once you call set valid, for example, on this MPLS 0, then obviously later if you check is valid, it will also be valid because now we made this header valid. So the validity of the headers can be changed at any time. If you look at the spec, it actually talks in a very detailed manner about how the validity is done. The authors of the spec made a particular choice that first you declare it valid, and at that point, if you try to read those values, they will still be undefined. So you'll get an undefined value, and then I write them in, and so at that moment, I know exactly what their values are. So it's just a matter how we decided to handle validity in the spec. So first you make it valid, effectively you add the header, and then you fill it up. The question was, what will be the values of the fields in the header if you make it valid? And the answer is, if it wasn't valid, they would be undefined. They will not be explicitly initialized, and that is mostly done for the efficiency's sake, so you can make your own decisions how you want to handle that. There is a question why VLAN tag in this particular case does not have an index. The answer is, I have multiple examples, so you can assume in some programs I had a header stack, sometimes I had only one, and for simplicity of the examples, I vary them from time to time. Can you use the last? No, you cannot. There is another method, which is, I think is called last valid, that you can use if you want to, yeah. Okay, let's move on because otherwise we might not be able to finish. So a couple more examples on the headers. For example, here I wanted to decapsulate an IP. Here what I do, I take when I decapsulate, what I need to do, I need to remove the outer header and make the inner header the outer. I basically copy the inner header, and copying a header is just another assignment operation in P4. So it's very easy, and then I invalidate the inner header, and that's basically all you need to do. Similarly, for example, if you want to operate on header stacks, there is a very common operations, push and pop. If I want to pop an MPLS label, there is a special method supported by the header stacks, which is called pop front. In this case, I pop a single label out, and the other labels are shifted to the left. And if I want to push a label, then there is a push front method available for the header stacks, which pushes everything to the right. The 0 slots becomes invalid, so I have to make it valid first, and then fill it up with my new label. So for those of you who were familiar with P414, you remember that there were special primitives to do that. So now these are just methods defined on the basic types, and you can perform all the operations on your own if you'd like. The last thing I wanted to show is some special bit manipulation operations that are available in P414. In both cases, we'll do the same thing. If you know, when you form the MAC address for the IPv4 multicast packets, it's 01005E and then the 23 bits of the original multicast address. So here I'm doing it using the so-called bit concatenation operation, that's plus pluses. So basically I take 01005E, it's 24 bits, one extra bit is also required by the spec, and then the 23 bits of the IPv4 destination address. And I think it's probably a better way to write the same thing is using the bit slicing operation. The nice thing about bit slices can be L values, so you can assign to a bit slice as well as you can take a bit slice. So here, that's exactly what I'm doing. I'm assigning 005E to the first 24 bits, clear up the bit number 23, and then the IPv4 address goes in there. That's another very, very useful feature that is available now in P416. The question is there an index with IPv4 header, I think, is that the question. It all depends on how you define your structure with your headers. If you define that IPv4 is a header stack, so you wrote IPv4 bracket 2, then it's a stack. If you said just IPv4, then it's a single element. Say, well, I can see you would define either a single variable or an array. Now, if you have, say, a title encapsulation, you can decide if you want to keep those headers as a stack or you want to keep them separate. I chose to keep them separate. Usually it makes things easier for the encapsulated headers. But if you want to use stacks, you can, absolutely. Inner IPv4 will be another member inside the header structure, which has the same type, IPv4T. When you do a pop, the contents of the index 0 becomes the previous contents of index 1. If index 1 was valid, then index 0 will be valid. If you want to make index invalid, you just use set invalid. There was a question of how to manipulate the stacks, and they're different. Definitely you can use push and pop if you want to, or you can use set valid, set invalid on explicit indices. Both are allowed, absolutely. This brings us to probably the most central construct of the controls, and that's match action table. We talked about match action pipeline, but notice how we didn't get to the tables before. And that's one of the important things about before. If you don't want to use the match action tables necessarily, if you just want to write an imperative program, it is absolutely possible to do. On the hardware that, for example, uses match action tables, the P4 compiler might encapsulate those actions into match action tables without any match, for example, or something like that. But you do not have to worry. You just write the code the way you would like to write it. What are match action tables? Basically, they consist of three most parts. First of all, you need to specify what would you like to match on and what are the types of the matches. Then there is a list of possible actions that can be executed if match happens or even if the miss happens. And then there could be additional properties that you can optionally specify. For example, the size of the table, the default action that you want to take if there is no match. You can initialize entries and so on and so forth. Each table consists of one of more entries or rows. That's how all tables typically are. And the entry will contain a particular value that you want to match on, a single action out of that list, so it cannot contain more than one action, and the action data, depending on what you need to do. So let's go through a very simple example of such a processing. That's how things are done. So here's the table. It's just an abstract table that you can have in the pipeline. And the important thing about tables is that the control plane has the interface. Usually those are auto-generated APIs that can be used to populate this table or to query it if needed. And the control plane is really responsible for inserting the entries in the table. Now, besides the regular entries, control plane typically would specify the default action and the default action data that will be used in case there's a miss in the table. Then the headers and the metadata arrive, and you can choose what you want to use to perform a lookup. So the chosen members of the metadata or the headers form the lookup key, and then that lookup key is used to look up the table. And then if the table is hit, then the action that sits in that entry and the action data will appear on some sort of a bus or something. Or if the table was not hit, then they will come from the default entry, so the default action and the default action data. And so obviously there could be some sort of a device that based on the hit will choose one from the other. And then what happens is the action will go in some sort of the action execution unit. Again, this is all very abstract, so all the devices are done differently, so physical structure might be different. But the important thing is that there are two types of parameters that are available to this action execution unit. I put them in different colors. They kind of look the same, but they really aren't. So one set is the data that came from the table itself. And I colored it green because it was the control plane that provided those arguments. And also, all the headers and metadata that you have in your program are also available to perform the actions. And so that little action code will execute, use two types of the parameters, and then put them back into your metadata or your headers or any other intermediate results. So that's how tables are defined in P4. That's how they work. What we will see later on is that there is a special syntax when we define actions, which allows us to differentiate between parameters that come from the control plane versus the parameters that came from the data plane. And that's where we'll talk about the direction of the parameters. If we look at some basic, maybe IPv4 forwarding situation, you can imagine a table that might be created by the control plane for this particular network, right? So for the address 192.168.1.1, we want to choose the action L3 switch, and that action might have certain action data like the port where the packet should go to, the new MAC DA, MAC SA, and so on. For the host 192.168.1.3, there would be a different action. We might want to drop the packet, and so on. So again, the table is populated by the control plane. P4 program typically does not know what's inside. The question is how this table will be mapped into the hardware architecture. The answer is there are many ways to do it. We'll probably talk a little bit about that in my presentation at the very end, well, when I talk about the device. But generally speaking, either a hash table in some hardware or in the software would be the way if you want to do exact match, and if you want to do LPM. Typically in hardware, we'll use a TCAM or algorithmic TCAM or something of that nature. And the compiler will do it, and we'll talk about that in a moment. The question is, how many lookups can you do? Can you do more than one lookup? The answer is, from the P4 perspective, a table is a single lookup. If your hardware is capable of doing multiple lookups on the single table, what you do, and I think that's the right thing to do, you define two tables in P4, but then the compiler knows that, oh, these two tables, for example, they can be merged together. And so the compiler backhand will place them into the same hardware facility. But from the P4, if you think about when you need to do multiple lookups, typically you use slightly different keys, you use different actions, like, for example, many people think about L2 table as having two lookups. In reality, it's really two logically separate tables. One when you do a lookup on the source MAC address, the other one when you do based on destination MAC address. You can merge those tables together in some hardware, and that's the job of the backend of the compiler to do this kind of stuff for you. So in P4, a single table is a single lookup. And if your hardware supports multiple lookups, the compiler will do a merge for you. So the question is, if you want to do two lookups in the same, for example, two lookups, one will be IPv4, another one will be IPv4 destination lookup, another one will be URPF lookup. In P4, and I probably didn't say it explicitly, but all the code you have seen so far is written sequentially, so you can understand that because we have only one brain, and I don't think we can understand the code written in parallel. So the semantics of all the actions and all the controls in P4, P4.16 specifically, is sequential. However, if the compiler can parallelize this on any particular hardware, the answer is go for it. And in reality, all the practical P4 hardware I've seen so far parallelizes things a lot. So on the paper or on the file, it looks like a set of sequential statements. In reality, it's actually very highly parallelized execution. The question is, if you define two tables, one for, say, source MAC lookup, another one is for destination MAC lookup, and the compiler merges them together, how will control plane see those two tables? The answer is it depends on the API generator that is done by the compiler backend. The API generator is something, and API generation is something that is not a part of current language specification, although we have the committee working on that to standardize it, but I would assume that whoever implements the backend will have an option of either generating two separate APIs for you or one joint API, and it's a choice. Let's try to go and define the actions for L3 forwarding as we used in the previous slide. This is a very simple action. I'll call it L3 switch. It's probably not how you would do it in a really practical way, because normally people use separate like next hop tables, but I decided to do a simple example. So when you use L3 switch packet, you typically send it to a given port. You replace the MAC addresses and maybe the VLAN ID as well. And so that's exactly what I would like to do. So to send a packet to a given port, we already saw that construct. You just set the intrinsic metadata. Here we modify the headers in place. And the last thing you probably want to do in the IP packet when you L3 switch it, you also want to decrement the TTL. And so that's pretty much the action. Now, please notice that these parameters do not have in or in-out specifications. They are, as we say in the spec, directionless. When the parameters are directionless, that means that they come from the control plane, or the other way around. All the parameters that come from the control plane are directionless. Maybe that's even better. Actions can take both types of parameters if necessary, but more often than not, in the actions that we use in the tables, typically they mostly use directionless parameters. So here's some other example. L2 switch is basically sending the packet to a specified port, and drop can be done as a mark to drop action that we saw before. If you want to have actions that operate on some data plane structures, then they will have directional parameters. So here's an example of such an action. So it basically takes a structure of the type L3 metadata T, and that is the structure that we defined here. This metadata exists in the data plane, so that's why it has a direction out. And then the next hop index is provided by the control plane. What you can do, you can use this action to operate on a variety of structures of the same type, L3 metadata T, so you can store the results in several places if you want to. Basically allows you to kind of have regular functions that you would have in the other programming languages. Here's another example when I set the L3 ECMP. So the only difference is I specify different next hop type in those actions. Now let's define our match action table. Let's define a table which performs the exact match on IPv4 destination address. The first thing we need to specify is the key. And so typically it will be a VRF and your destination IPv4 address. That's all we need to do. We need to specify the fields and the type of the match, which is exact match. Then we specify a list of actions. So this table will have 4 different actions. So L3 switch, L3 L2 switch, drop, and no action. Each entry will be able to choose only one of those actions. And we can specify what the default action will be. In this case, I decided to say no action. So if there is no match in this table, don't do anything. And we can specify the size if we want to as well. And that's how the table will kind of logically look like. So this is the key portion, the VRF and the destination IP address. This is the action for a given entry, and this is the action data, which depends on which action we chose. The question is, if you decrement the TTL in the IP header, when do you update the checksum? The answer is, we'll talk about that later in this presentation. Now, suppose we would like to define a routing table. It's actually very easy. The only thing I need to change is the match type in the key section. Now I decided to use the LPM match on the destination IPv4 address. I added some extra actions, and I showed that if I'm using actions with directional parameters, I need to specify the parameters right here, because I need to say to which particular structure I want to apply this action. And this is how the table will look logically. Now it has the VRF, but the IP address is specified with the prefix length. And so that prefix length, the control plane will probably also use to put the entries in the right priority. Suppose you want to go really fancy, and you want to do full ternary match on both VRF and destination IP address. So that's also easy. We just again change the match type to ternary. And now our table will logically look even more complex, because now we'll have the value and the mask in each of the entry, and we also have to specify the explicit priority. And again, it's the control plane's job to do that. Now when we define the table, we can use it in the control. And that's how we will do it. We'll declare all our table and actions in the beginning of the control, similar to how when we write in C, we first declare our variables and stuff like that. And then we have our apply block, which is really the code for the control. Or you can say it's declaration of the apply method of the control, if you want to be really object-oriented and formal. And in there, we'll apply one table that we declared before, maybe the table called assign VRF. And then we'll also check if IPv4 header is valid, then we'll apply our v4 host table. In other words, to perform this match action operation on the table, what we need to do, we need to call the table's apply method. And that's how this is done. This is different from P4.14, where apply was a special statement. Now it's just a method on the table object. Can you define action inside the big apply? Can you call an action? Yes, absolutely. That's what we did on the previous slide, remember? The question is where the directional arguments for the functions come from. The answer is the directional arguments, these are just objects that you have on your data plane. So, for example, in this particular case, let me go back to the previous slide. What I said is I want to apply my L3 switch next hop action to L3 next hop info structure in my metadata. Think about meta is a struct containing some other structs, and one of those structs is called L3 meta. Okay? That's what the directional parameter means. So it has nothing to do with intrinsic metadata. It's just a convenient way to apply the same action on different pieces of your own metadata. To reiterate, in order to perform a match action, what we need to do is apply the table. Now, when we perform the match action, there are some results that are kind of generated, which I would call meta results. One of them is, was there a hit or miss? And the other important result is actually the action that was chosen. To do that, there are special methods that can be used as a result of this apply. So let's take a look, for example, at this piece of code. What I'm going to do here is I will apply the IPv4 host table first. And then the apply itself returns kind of a pseudo-structure. One of the fields there is called hit. So I'm saying if apply hit, actually if there was no hit, then I want to apply my LPM table. It will not be at 2 stages in the pipeline, actually, because if you think about how the match action happens, match and actions, they are separate stages, really. Not stages, separate steps. Let me be clear. Separate steps. So once you've performed the match, after that you need some time to apply your action. So on at least some parallel hardware, the way these things will be done, it will be done as speculative execution. So in other words, most probably the compiler will transform the program in such a way that match will happen in both host and LPM tables in parallel. But then, if the host table hit, then the results of the second match will be just thrown away, because in the hardware, it's much easier to throw away stuff rather than do things sequentially. Tables can have totally different nature, and again, it's up to the hardware to make sure that this is possible to do, but that's what happens in many cases. Here is another method of or the other property of the apply that P4.16 provides, and that's called action run. So action run returns a special enum corresponding to the action that was chosen from the table, be it a default action or an action from an entry. And so here what happens is based on the action that was in the entry of the IPv4 LPM table, I can choose where I go next. So, for example, if the action was switch next hop, then I probably need to apply my next hop table. If the action was switch ECMP, I need to do a lookup in my ECMP table. And if there was a drop, I will use a special operator called exit, which means I want to go right to the very end of my whole apply block. And so that's very useful if you decided to drop the packet and you don't want to do any processing. It is basically a go to the very end of the top level control. This construct also allows you to do speculative execution if you want to, because again, you can perform match in all the tables at the same time, and then if the action that was chosen from my PV4 LPM was not one of switch next hop or switch ACMP, you'll just ignore the results of those matches. What match kinds are available in P4? So match kind is really a special type in P4, which is similar to how we saw the error one. It can be augmented, but not by the user, but the architecture. So the basic ones that are defined in the spec are exact, ternary, and LPM. But for example, if you look at the V1 model definition, it also adds different new match types like a range or selector. And you can imagine that other targets might decide on some other match kinds. I just decided to be kind of creative here. So it could be a reject type match, or it could be a range, or it could be some fuzzy match. We don't know. Each architecture is allowed to add their own match types in addition to those defined in the core language. Probably the last thing I wanted to mention about the tables are the fact that you can also use expressions when you form your key. For example, one of the most popular ones is valid. If you try to match on a header which is not valid, so you basically try to read out the values out of the invalid header, you don't know what you will get. It usually makes sense to either check and ensure that you're matching on something valid, or when you perform a match inside the table, you can also match on the validity of the headers. And here's what I'm doing here. I match on the Ethernet address, both destination and source, and also on the validity of the tags. So what I was trying to do here is I was trying to define a table which performs the initial classification of the L2 packets into a variety of categories. Some of them will be just malformed, and some will be very specific. So single tagged unicast packet, untagged unicast packet, and so on and so forth. That's where I really need to perform the check to see how many VLAN tags I have in the packet. And with that, I wanted to demonstrate another property that is allowed for the tables, and that property is called entries. What it allows us to do, it allows us to initialize the entries, because the tables like this one most probably has to be just initialized once when you load your program, and I wouldn't imagine control plane manipulating it very often. Here's how you can do that. You can define your entries, and they can also have the const attribute. In fact, that's the only thing that the compiler allows right now. And you can say, well, if my destination address is all zeros, that packet actually, as we know, is invalid, so we'll mark it as malformed. If my source address is zeros, it's also a malformed packet. If, for example, the source address is a multicast address, so bit 40 is 1, it's also an invalid packet, so we classify those. If the destination address is a broadcast and VLAN tag 0 is not valid, it doesn't really matter, because VLAN tag 1 probably is not valid either. So it's an untagged broadcast packet, and so you can subsequently have the definition for single and double tagged broadcast packets. Then we can say, well, if just the bit 40 is 1, then this is untagged, single tagged, or double tagged multicast packet, and so on you can do for unicast. So you can initialize the tables and obviously save you from some control plane programming and make sure that the tables are always initialized by the compiler. The question is, what is the priority of this initialization entries? And the answer is the priority is textual. Think of this as a linear search. And so obviously we'll hit the last 3 entries only if it's not multicast and not broadcast. So the other thing I wanted to point out, there is an operation 3 ampersands that actually defines a special type in P416 called a cube, which is basically the multidimensional kind of set of values, and underscore stands for everything. So these represent sets. Yes, the question is, if you initialize the tables, can you change it on the fly? So for now, we decided that you will not be able to, and that's why I put the const in there. And the reason is, if you want to be able to change the table on the fly, then there should be a very tight interaction between the compiler and the control plane. So for example, you would need to know the IDs of those entries and things like that. And so for now, we don't really have a good way to express it, so we decided that we'll stay with the entries that cannot be changed. The question is, what will happen if header is invalid, how the match will work? So the spec says very clearly, if the header is invalid and you try to read it, you don't know what you'll get. It's the same thing like in C, right? If you try to read an uninitialized variable, you don't know. No, there will be the lookup will not be skipped. If you want to skip the lookup, then you skip it explicitly. Like for example, I did before. Remember that, let's go a couple slides back. Like here, I said, if header IPv4 is valid, then let's apply these tables. And that's very important that you do those checks. Normally, when you have a real program, you will do them in the beginning, and it's not like you will predicate every table based on the validity of headers. It only happens once in a while. Now, we learned how to parse the packet. We learned how to write our code that processes the packets. And now, I want to talk about deparsing. Packet deparsing is actually a very simple procedure. All you need to do, you just need to output your headers in the right order. Because it is just straightforward linear procedure, you can use the regular control to do that. The only difference is that the arguments for this control are different. So now the core library provides us with a special extern called packet out, and that will represent the byte stream that we're trying to assemble. What we'll do is we'll take the structure of the headers that we processed and we'll put them out as a packet. And here how it will look like. Based on the discussions we previously had, you will emit the Ethernet header and the VLAN tag. Now, the important thing about this emit method is it will emit the header only if the header is valid. So if you made the header invalid previously or it was not in the packet, nothing will happen. Okay? I assume Ethernet header probably was there, so it will be there, first one. Then if VLAN tag, and it could be either a single header or it could be a header stack. Emit takes both. If VLAN tags were there and we didn't remove them, they will be emitted. If they were not there, nothing will happen again. Then you probably will output the stack of your MPLS labels. Again, they might or might not be there. And so it's a very safe code in that sense. And then we'll get to layer 3. What I'll do, I'll emit ARP, IPv4, and IPv6. Now, obviously, this doesn't make any sense. But in a single packet, you typically either have ARP or you have IPv4 or IPv6, right? So that's why, out of these 4 statements, either the first 2 will be executed, like will have any effect, or this one or this one. And then we'll get to emit layer 4. So these deparsers, they're very, very easy to write. In fact, we can either simplify it much better. So if you imagine that those headers were in your myHeader header structure exactly in that order, all you need to do, you just can say packet emit header. And whichever headers are valid inside that struct, those will be emitted in exactly the order that they were defined. So deparser might have a very, very short code. To answer the previous question from Anupam, whether deparsers and parsers are coupled or decoupled, the answer is they're totally decoupled now. So you can output headers in any way you want, however you want to do that. There is still a question that I didn't cover, is how we'll recalculate the checksum. I'll answer that question when we get to that slide. Yes, I will. The question is, can you have conditional statements? Theoretically, yes. So you can definitely write if statements. And as you see, this is a control. So everything we discussed before can be used there, at least from the language syntax standpoint. Now, what the particular architecture and particular hardware will allow you to do, that's a separate question. Because normally in the hardware, the actual structure of the deparser is different. So they might not allow you to use fancy if statements, or you might not be able to do table match and action and stuff like that. But from the language standpoint, and it's actually a very important point, you can use any construct anywhere. And as hardware develops and becomes more powerful and more regular and so on, you will be able to consume all these features without the need for the language committee to do anything about that. If today, for example, Deparsers only allow you this very linear specification, that's okay. Tomorrow they will allow you to do other stuff. You will just use if statements and so on. And that's why we believe that P416 will be able to stay there without changes for quite a while. We might add something, but there are no particular rules that say that what you can or cannot use any particular control. Now we'll talk about the other feature of the language, which does a lot of magic and is even more, I think, responsible for our belief that the language will remain quite stable. And these are externs. By now, we stayed within the confines of the core language, but even there, we had to use some externs, this packet in and packet out. And so the truth is that they kind of representative of a big class of objects that are now allowed in the language. We just have to admit unfortunate truth that all the platforms, all the hardware, they typically have a lot of specialized components that we cannot really express, and we should not be expressing using P4 itself. If we can express, then they become actions or controls. But many specialized computations, many very secret sauce things just cannot be expressed that way. If you remember my previous diagrams, those were little shiny gadgets in there. First of all, they're very different than from vendor to vendor. Different vendors provide different things, right? As I mentioned, you cannot really express them in the core language because they perform some difficult computation and so on. And the other thing that we'll talk about extensively is they might also have a special state that is accessible by the control plane. So tables have such a state, but externs can have the state too. And at the same time, there is a big desire for us to keep the language the same. So in P414, a lot of elements in the language were dedicated to these externs. And now, in P416, we basically removed all these specialized objects from the language and made just one unified mechanism to express them all. Because, and I repeat myself, in order to consume an object, you don't need to know what's inside. You just need to know what the interface is. And it's not like my idea. It's what object-oriented programming is also about, right? Now let's see how we can do that. So there are two classes of objects that we have in P4. I will call them stateless and stateful. So stateless objects, they are mostly variables and the metadata and the packet headers. So every time a new packet comes in, they are reinitialized. So they do not keep the state from packet to packet. And at the same time, we have a need to have stateful objects. So the most interesting processing usually happens when you use stateful objects. And one type of such objects we already learned, those tables, right? They keep their state from packet to packet. The nice decision I think was made in P416 is that there are only two kinds of stateful objects in the whole language: tables and externs. If your hardware has something that keeps the state, it will be an extern. In real hardware, we have a need to have a variety of such objects. So counters probably come to mind first, right? They keep state between packets. They increment every time, either by one or by the length of the packet. Meters are also stateful objects. They have to keep their state in between packets. And then in P414, we had a generic construct called the register, which allowed us to store and retrieve any kind of information in the data plane. This table kind of summarizes their difference, and you could see that one of the important things is they all have a certain control plane interface, and we'll talk about when we instantiate those objects how it helps to achieve that. So let's see how we can use counters. This is probably the most simple stateful object that I can think of. And so in V1 architecture, obviously we do have counters because they're such an important part of any data plane program. The extern definition for counters and for any other extern contains a couple things. First is the instantiation method. Here, the instantiation method has the same name as the name of the extern, and it can take some parameters. And the way to think about instantiation methods is really the function that is evaluated at the compile time. And the other piece of the extern definition is basically a set of methods that we can use together with this extern. In this particular case, you could see that the counter extern uses a certain type called counter type, and it's also defined in the architecture file. It is another type that we didn't talk about much, but it's in P4.16 is called the enum. Enum is kind of a set of values which do not have any particular hardware or numerical or any kind of representation. They're just set of allowable values, so to speak. So this is the definition of the counter extern in P4.16. You don't have to write it. It's already written for you by whoever wrote the architecture definition, in this case, v1model.p4. Now let's take a look at how we can use these externs. The first thing we need to do is basically instantiate the extern inside the control. So here's our control. And here how we instantiate the extern. Remember, it had two methods. So one was the instance count. The other one was the type. So the instance count will be 8K. And the type will be this enum, so counter type, packets and bytes. And the instantiated instance will be given a name, ingress, bridge domain stats. The importance of this is is such that if you instantiate the object and you give it a name, then it is possible to generate the control plane API that will refer to this instance by name and be able to access it. So for example, we'll be able to auto-generate the APIs to retrieve the counters. This object is here, and remember it had a single method called count. So in the compile time, basically the compiler evaluated this instantiation, and what it did, it creates an array of 8K counters somewhere inside the hardware. Now what we can do, we can use the methods in our actions, or we can use them directly. So here I just decided to define an action called setBridgeDomain. And one of the things that we'll do, it will take an argument called bridgeDomainStatIndex and increment the counter at this index inside ingress BD stats. You could see this, the last line in the action definition. Now you can define a table which will use this action, setBD. And effectively what will happen when the control plane programs it, one of the action data that it will set for the setBD action will be a BD stat index. And so if you have, like, for example, two entries with the same index A, they will point and increment the same counter in this table, or it could be another entry with the index B, it will increment a different counter. So basically you get a flexible scheme. The index of the counter, in this case it came from the action data, but it could be computed using any kind of formula. So only your fantasy is the limit, what you can do with that simple extern. The question is, how would you know that the counter is an extern? I think the answer is because this is not a reserved word in the language. It's just the name of the extern method. And that extern method came from a file called v1model.p4. The name of the extern is basically defined by the vendor, whoever defined the architecture for you. The extern keyword is used to define the extern. And this is not the definition of the extern, this is the instantiation of that extern. Right? So same way when you call a function in C, you don't say function printf blah blah, right? You just say printf. So same thing happens here. It's just a matter of syntax, but I think we don't need a special keyword to specify that we're instantiating something. The question is, count method that we used in the action, the real method or not? And the answer is, based on this definition of the extern, it's a real method, right? Because you really want to increment the counter at that particular index. So there is no other way to specify that. You really have to explicitly call this count. Because otherwise, which index you will increment inside that array? You have 8k different counters, and you need to choose which one you want to increment, and you just one counter. The question is, how do we know that this count method does something? The answer is, when you get the library of your externs from your vendor, that's where those methods are being documented. And so it says, and obviously in the in the formal definition, we can only see this as on the previous slide. The formal definition is the object, the extern counter, has the count method. You cannot really say what it does. I agree with that. But when you read the documentation, you will know that the count method increments the counter, and because the counter has the type of packets or bytes or packets and bytes, it will do a certain thing. The question is how many counters you can update and how big can be the action data. The answer is it really depends on your platform. It really depends on your hardware as well, right? So in the language per se there are no limitations. When you get to program a certain chip, you will know it can do only so many counters at a time and so on. The question is, can you retrieve the counter value inside the metadata? As I mentioned before, so the count method just accepts a certain 32-bit value, right? So it can come from anywhere. So it can come from the action data, or it can come from some metadata and could have been calculated way earlier based on I don't know what. So this is totally okay. In terms of the other things, obviously you can instantiate multiple different counters, right? So you can call the counter instantiation method multiple times, and so that will create multiple arrays, and then each of them can have their own independent index and so on and so forth. So again, from the language standpoint, you have full flexibility. From the real life standpoint, it's whatever your actual target and your actual architecture will allow you to have. Similar to counters, there are also meters. I think someone was asking me about policing the traffic. V1 architecture defines another type of external object called meters. So this is the definition. Again, when you instantiate the meters, you specify the instant count and the type of the meter, which means that we want to meter either on bytes or packets. And meters have only one method, which is execute meter. And what this method does, it basically calculates the color of the packet. And if we're talking again about V1 architecture specifically, it encodes that as I put here. So green is 0, yellow is 1, red is 2. On any particular hardware, on any particular architecture, the encoding could be different. And here's how we can use it. So here I decided to define a type using the type def construct we discussed earlier. So 2-bit value of the meter color, defined my constants, instantiated the meter. It all happens under the control, but you know, I hope you got the hang of it on all the previous slides. And then I just decided to have a function which calls the execute meter method. And so what it does, it basically calculates the color of the packet and stores it in the meta color. So it's a field in some of my metadata structure. And then what I can do is, for example, I can have some ACL table. In there, I will use one of the actions will be color my packets. And then later on, I can say if the color of the packet is red, mark it to drop. So meters themselves do not perform any dropping or anything about the packets. They just determine the color of the packet, and then you use your normal control structures, ifs or tables or whatever else you want to do something about that color. The question is, can you use these meters for hierarchical metering? The answer is yes. What you do, you instantiate 2 different meters for level 1 and level 2, calculate the colors in 2 meters, and then use the logical operations to decide what the final color of your packet will be. The meter provided by the architecture is not hierarchical. It's a 2-bucket TRTCM meter. But if you create 2 meters, and then you can have your hierarchical meter with 2 or 3 or 10 levels of hierarchy, depending on how many of you created. And that's a very important thing, right? Instead of having some very specialized constructs, which will be only useful in one particular instance. It's much better to provide the building blocks out of which you can build whatever you need. And you can be very creative. For example, think about this. Instead of using the meta color as the output of the meter, I could have used any 2-bit field or any other field inside the packet header. And so the packet will, for example, get out and carry the color as computed by the device in its own header if I wanted to. And it's really only your fantasies limit what you can do. The last stateful object in V1 architecture that I wanted to show you, that's a register. So there's the most generic ones. And here's how the definition looks like. So there are two methods in addition to the instantiation. So one is to read the register, and one is to write the register. Fairly obvious. And so what I will try to do here, I'll try to calculate the interpacket gap within the flow. It might be useful for if you, for example, want to do some kind of flowlet switching. So if you would assume that if you have a constant stream of packets, it's kind of one microflow, and then if there is a pause, then probably it's a slightly different thing that's going on. And so to do the interval, what I will do is I'll store inside the register the time the previous packet arrived, and then just calculate the difference and output somewhere, and then store the current time. And then obviously you can have some other calculation if the difference exceeds this threshold and do something. Here's the action get interpacket gap that I decided to define. So I already defined my registers. And what I will do is basically read the value of the register into the temporary variable that I created right inside the action called last packet timestamp. Then I calculate my interval by basically just subtracting that last packet timestamp from the timestamp inside my current that my packet arrived with. And then I store the current timestamp in that register. And the interval, as you could see, that is the output parameter of this action. So we can use this action and then get the interval out and do something else in the outer control. The question is, can control plane access registers? The answer is yes. If you look at the table I had on slide 69, you could see that for the registers, I said in the data plane we can read and write them, and the control plane has full access, right? Whereas in meters, for example, we can only execute meters, but in terms of the control plane, we can specify the configuration, but we typically cannot read the state of the buckets and stuff like that. So it all depends, obviously, again, on your architecture, but generally speaking, or in particular with V1, that's what it is. Here, I wanted to show you a slightly different type of an extern that allows us to extend the tables. And that's also allowed in P416 because tables can have custom properties. So in this particular case, I'm referring to the externs called direct counters. So this is how they are defined in V1 model. Very similar to how the regular counters are defined, but the type is different. It's called direct counter. But their usage is somewhat different. Here I declare my direct counter. And as you see, I do not specify the size. I only specify the type of the counter. And then when I define a table, like for example an IPACL table, I specify the additional property called counters. And so in there, I refer to the extern I've just created. So what it does the following. So imagine your ACL table. I showed it on the, which one is left-hand side. It has certain keys and certain action and certain action data. And when you define this counters property, it basically kind of got extended. So every entry gets an additional piece. It gets an additional data portion, which is our counters. In this case, it's packet and byte counters. And then what happens is I can actually use the count method inside the actions associated with this table. So for example, if I have an action called ACL deny, I will drop mark the packet to drop, but I also can call the count method of the ACL counter. And so what it will do, it will allow me to count the packets I just dropped. So these counters, they do not live outside of tables, they live inside. So syntactically, one thing that you need to remember is in P416 there is no really syntactical difference between these types of objects. And again, it's really a matter of the architecture definition and documentation, which will tell you which counters can be used where or which objects can be used where. Besides all these stateful externs, there are also externs which typically do not need a lot of state or do not have a lot of state. And so I just wanted to show you how to use externs to do some custom computation. So computing a hash is a very common thing because we wanted to compute flow IDs or something like that. This is how the hash computation is defined in V1 model. Actually, I simplified this definition a little bit for clarity. Basically, we define an enum which specifies the hash algorithms that are available to you. And then there is an extern just defined as a function. So the function name is called hash, and it's templatized. It outputs a result of a certain type, and it takes data a certain type and also hash algorithm and min and max. And so if we want to compute, for example, a 10-bit flow hash, what we'll do is this. If you have an IPv4 header, then we will call our hash function to output this flow hash based on CRC32 algorithm. And that is the set of headers, this type D in the template, that we will provide. If we want to compute flow hash for IPv6 packet, we will use a different algorithm here and provide a different sets of fields. And otherwise, we can compute a flow hash for an L2 packet and use another set of fields. So what happens is the same thing like you use templates in C++, right? So what template is, it really generates a function of a particular type at the compile time for you. This hash function definition is pretty much like that. There's a template, and then the particular function with the correct typing is generated based on the call. Just for your reference, in V1 there's also a nice extern to generate random numbers as well. And there is a extern which generates checksums, specifically 16-bit checksums. And the reason I wanted to show you this extern is because that's how we can calculate and recalculate IP header checksums. So those of you who asked, I promised, it's there. This extern is slightly different, as you could see. It actually has the instantiation and it has the method. And there is, I mean, again, it's really up to the designer of the architecture how to do that. There is no reason why, say, hash checksum calculations cannot be instantiated as well. It's up to the architecture definition. This is how we can do IPv4 checksum verification, first of all. Using this extern, we'll have a special control, and this control is defined in V1 architecture called checksum verification control. It receives the parsed headers as the input parameter and outputs the metadata. What we do is we instantiate the checksum16 extern to calculate IPv4 checksums, and if the IPv4 header is in the packet, we'll basically calculate the value of the checksum using all the fields that should be inside that checksum. And then we check if this checksum that was calculated is the same as what was carried in the header. If it was not the same, I'm sorry, then we mark the packet for dropping or do something else. If you want to update the checksum, again, what you do, there is a special control, and you again instantiate the checksum16 extern, and then if the header has if you have the IPv4 header in there, then you go calculate the checksum over all the fields that you need to calculate it over and put it right into the IPv4 header checksum field, and that's how you update the checksum. The question is how this will be implemented depending on the hardware, I think. And the answer is really different hardware does it very differently, and the compiler backend should be very acutely aware of which hardware it compiles. From your standpoint as the P4 programmer, you need to express what you want to do. And you want to calculate 16-bit checksum over these fields in this order. The compiler will use whatever the hardware facilities are provided by your target to do it the right way. The question is, do you do it before or after the emit? I would think you do it before the emit, of course, because you want to update the checksum. Now, in some architectures, in this particular case, you saw I wrote a separate control for this. And that's how V1 architecture is defined. So V1 has multiple controls. And so one control is specifically to update the checksums. In your architecture, it might be that you want to do it right inside the deparser control. That's also possible. From the language standpoint, there is no reason why you would not instantiate this inside the deparser and do it right before the emit or within the emit, or maybe you'll have a special checksum emit, which does just this. So it's really up to the definition of your particular architecture. Now we pretty much looked at everything, and now it's the time to kind of get the whole program together. And Prem also shows me that, I should be real quick with this. Right now, P4 programs are compiled as a single modules. But if you want to structure them, before we compile P4 programs, we put them through C preprocessor. And it's also defined in the spec that we support C preprocessor directives in P4. That's how you can structure your code. And the only other rule is you have to define your objects before they can be used, which is also normal practice. So here's how the program should kind of look like. And when you go to do the labs, you will see programs written in that style. So first, I recommend you put this line in the beginning, because this basically line indicates the Emacs mode. And we've already designed the modes for both P4 and P4 14 and 16, so it might be a nice thing to do. Then you include the core language library, that's core.p4, and you include the P4 files that you need to include for your architecture, so V1 and so on. Then you can define your types. You can define your constants. And here you can define the top-level controls and parsers that are prescribed by your architecture. These are specific objects that are prescribed by V1 architecture for you to have. So there is the parser, there is checksum verification control, there is ingress pipeline definition, egress pipeline definition, checksum update, and deparser, so 6. And the last thing you do, and this is the new construct, you assemble a package. The package is a new term in P4, but remember there was a question, how does the code know which function to call? Well, that's because you specify them all in that package construct and you name the package main. That will tell the compiler that this particular function represents your parser, this particular function represents your ingress pipeline, and so on and so forth. So inside the architecture definition, there is a templatized definition for this package called V1 switch in this particular case. The order is defined by the architecture. So the architecture says the first argument should be the parser with these arguments, and it's templated. The second should be a control, the third one should be a control, and so on and so forth. So the order in this definition does not necessarily mean that they will be called by your architecture in that order, though most probably the designers of architecture will make the order sensible. It's really up to them. I think we're right at the end. So I guess we discussed what are the advantages of using P4. So you saw there was a very clearly defined semantics of the language, and you could see what's happening. The language has a lot of new ways to express what you want to do in the data plane using a fairly small number of constructs. It is a high-level and target-independent language. We also saw there's a lot of type safety checks, so all the parameters now have their types. And I didn't mention it, but you probably saw in some of the examples I used the casts to do things properly. And obviously, through that, you can be very agile in your data plane development. We didn't get to that a lot, but I sort of mentioned that you can always move the data back and forth from the intermediate results in the packet headers. So you can create a lot of telemetry solutions. That's what we covered. So how the P4 looks at the world, how the data plane processing done, and the separation of language, the architecture. I want to impart it again, how important it is that really you don't need to be able to express everything in P4. As long as you can express the interfaces, you can consume a lot of interesting components, and that allows the language to be really, really stable. I think that is the main innovation of P4.16, if you ask me at least. We covered the data types, the parsing constructs, the control flows, deparsing, and the program structure. There are some things we didn't cover, but they will be in the presentation that you will see it on the web. The reason we didn't cover is because Prem showed me that it's time. So there are mechanisms for modularity, so you can define your own custom controls and call them from your own controls, so that allows you to have a better program structure. We didn't discuss the variable length field processing details. I didn't discuss a lot of details about V1 architecture, how to do cloning and such, but I just mentioned that, right? So that it's done mostly by setting the proper intrinsic metadata fields. We didn't have time to discuss other architectures, but they will be forthcoming. And we didn't discuss some of the latest constructs in the language, like header unions, which are very, very useful, and probably we'll do it next time. Also, we didn't discuss the control plane interface, and you'll be able to try it during the labs. That's pretty much all I have for you, and I think we're right on time. Thank you.